Hello students, welcome back to Vastiversity. Today we're going to be continuing with exponential growth and decay. So in many natural phenomena, quantities grow and decay at the rate proportional to their size. Right, as we talked about last time, we did some economics problems, some bacterial growth. So there are laws of growth and decay. So in general, right, if y, right, is a quantity at time t, and if rate of change of y with respect to t is proportional to a size, then we can use this equation, right? We can use this equation, dy over dt is equal to k times y, where k is a constant, right? Essentially the growth constant. In this case, we are, the natural growth, we will assume that k is actually greater than 0, right? Or this is going to be the growth, right? Growth. And decay would be k less than 0, right? That would be decay. So let's say chemical components decay, right? Radioactive decay would be k to be less than 0. And so the equation that describes this process is called differential equation. So differential equations is a very big topic in the entire mathematics, and we will have multiple playlists describing the ordinary differential equations, partial differential equations, fractional differential equations, and stochastic differential equations. So the links are going to be attached in the description. All right. So it's, it's not too difficult to think about the first equation, and of course, we can think of an equation that actually produces such solution, right? Such solution as we have it here, and it's going to be our theorem, right? So theorem 2 is essentially the only solutions to the differential equation, dy over dt is equal to ky, are the exponential functions, right? Where y naught, so y of 0, we call it initial condition. So we might have multiple different functions, but here, when we're forcing an initial condition, we will have a specific growth function or decay function based on the k itself. So the first thing is, of course, the population growth, right? So population growth, we can have something like this. So population growth, we can have an equation dp over dt is equal to kp, right? Or also in common ways to rewrite is going to be 1 over p times dp over dt, which is equal to a. Okay, so we call it also a relative growth rate. So let's take a look at this example here. So let's see. So use the fact that the world population was 2,560 million in 1950 and 3,040 million in 1960 to model the population of world in the second half of the 20th century. Assume that the growth rate is proportional to the population size. What is the relative growth rate? Use the model to estimate the world population in 1993 and to predict the population in the year 2020. Okay, so we will see how accurate. So essentially, back in 1950, that was 2 billion people, right? 2.5 billion, essentially. And then in 1960, it was already 3 billion, right? Billion, so pretty big number. So let's go ahead and so we will assume that p of 0, so initial state. So initially, our population was 2,560 million, okay? And then p10, right, 10 years later, right, because it's 10 years gap, it's 3,040, right, million. Okay, so now, by using the second theorem, so by theorem 2, right, what are we going to have? We know that p of t is equal to p naught of e to the kt, which is equal to, so 2560 times e to the kt, right? So we do not have a k, but we do need to find it. So we're going to use our second condition. So now p10 is going to be equal to 2560 times e to the power of 10 k, right? So, and that's equal to 3040. So, solving for k by using logarithms, right, we're going to get that k, so 10k is equal to natural logarithm of 3040 over 2560. So that means k is equal to 1/10 of natural logarithm of 3040 over 2560. So that's going to be about, right, we're going to approximate it to be 0.017185 by using calculator. Okay, so that means that our growth model, so essentially in a percent wise, the relative growth rate is about 1.7% per year. Right? That's the relative growth. And so the model, E of t, is now 2560 times e to the power of 0.017185 times time. So now we can predict population in each of the upcoming years. So population at after 43 years, which is 1993, which is 2560 times e to the power of 0.017185 times 43, going to be equal to approximately 5,360 million, right? So, or 5,300,000,000, essentially. And then P70, right? So in 2020, we have 2,560 times e to the 0.017185 times 70, which is about 8.5 billion. So 8,524 million. Right. So we are, we can see that as we go, the data might not always be, we might not always hit the prediction, right? We are in 2020, we're just short of 8 billion. So we are off by 500 million, essentially. So, okay, but here would be the graph, right? Population in a million and years as years grow, right? But of course, the full differential equation, if we would want to have it more complicated and include different factors, it would not be an exponential, right? But this is a very crude approximation. Okay, so we can do a very similar problem, right? Very similar problem, but for decay, right? Because this was growth. Now we're going to talk about decay. And of course, chemistry will help us out. So let's take a look at this example. So the half-life of radium-226 is 1,590 years. Part A, a sample of radium-226 has a mass of 100 milligrams. Find the formula for the mass of the sample that remains after t years. Okay, so part A. So we're going to say that, we will say that M0, right, initially we have 100 milligrams. Okay, so by our second theorem, theorem 2, gives us that M of t is going to be M0 times e to the kt, which is equal to 100 times e to the kt. Okay, so we know that the half-life, meaning that we're going to have half of what we have so far, happens every 1,590 years. So that means 100 is equal to, right? So not 100. 100 times e, so m of 1,590 is equal to 100 times 1,590 times k is equal to 50. Okay, so that means that 1,590k is equal to natural logarithm of 1/2. So K is equal to, by using the rules of logarithms, we're going to have a negative ln of 2 over 1,590. Okay, so that's going to be our K. So this time, let's keep it as it is for now, right? Because we will want to simplify as we go. So that means our equation, right? Our equation, m of t, is going to be equal to 100 times e to the power of negative ln of 2 times time over 1,590. So by using the rules of exponentials, we will get that our equation is 100 times 2 to the power of negative t over 1,500. Okay, so that's going to be our formula. So part B, find the mass after 1,000 years. So 1,000 years, so B. So m of 1,000 is going to be 100 times e to the, not e, actually, I'm going to use 2 to the negative, right, 2 to the negative 1,000 over 1,590. So that's going to be about 65 milligrams. Okay. And then, when will the mass be reduced to 30 milligrams? Okay, so roughly, so C, we want to find the opposite, right? So we want to have the following. We want to have that 100 times e to the negative ln of 2t over 1,590 is equal to 30, right? So when does that happen? So if we solve for t is going to be negative 1,590 times ln of 0.3 over ln of 2, which is about 2,762 years by using the calculator. Okay, so essentially, that's when that will happen. So those kind of problems are very common and they are pretty accurate. So that's how, for example, chemists find out about the decay rates, right? And predicting how the decay will occur. Not only in the chemicals, but also in the astronomy, how the stars can decay. All right, so the next one's going to be the Newton's law of cooling, right? The Newton's law of cooling. So essentially, that's also a very interesting equation. So let's go ahead and move on. So Newton's law of cooling, also related to differential equations. So it essentially states that the rate of cooling of an object is proportional to the temperature difference. So dt, so which is capital T is the temperature, over d time, is equal to k times temperature T, which is a function, minus T of S, right? So essentially, right, T of S is going to be the constant, and it's the temperature of the surrounding, right? So T sub S, temperature of surroundings. Okay, right, so for example, if we would do it in the room temperature, that would be about 20 Celsius or 72, 73 degree Fahrenheit, or 293, about 293 Kelvin, right, depending on the units that we want to use. So, for example, let's use that equation, right, to do the following problem. To do this problem. So, bottle of soda pop at room temperature, 72 degrees Fahrenheit, is placed in the refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the soda pop has cooled to 61 Fahrenheit. So, part A, what is the temperature of soda pop after another half hour? Okay, so first we want to find an equation, right? We want to find an equation and compute that equation. So, okay, so let's use the Newton's cooling law. So we're going to have dt over time is equal to k of T minus 44 Fahrenheit, right? So we have to keep the units. So, okay, now we know that our t sub s is 44. So let y to be t minus 44, then y naught is going to be t naught minus 44, which is 72 minus 44, which is 28. So we're going to change that equation, right? If we take a derivative of it, it's just going to become dy of dt over dt, right? It's going to be dy over dt, which is dt over dt. So plugging that back into the equation, we will get that dy over dt is equal to k times y of y naught to be equal to 28, right? So we transfer that equation into something we know how to solve, because this one's going to be a little bit complicated to solve, right? It's something we do not know. Well, we kind of know, but we kind of do not know what kind of function will give us that expression. So we would better be safe in this case. Okay, so by the theorem, right, by theorem 2, we will have that y sub t is equal to y0 times e to the kt, which is in our case going to be 28 e to the kt. So we are given, right? We are given time-wise. So t after half an hour, right? So we're going to do it in minutes, right? So 30 minutes. Okay. So 30 minutes, we're going to have that it's equal to 61. So that means y of 30 is equal to 61 minus 44. We have to scale it back, so it's 17. So that means 28 times e to the 30k is equal to 17. So that means 30k is equal to ln of 17 over 28. So k is equal to 1 over 30 times natural logarithm of 17 over 28, which is about negative 0.01663. Okay, so yes, temperature is decay. So our y equation, right, specifically, right, keep in mind, y of t is going to be equal to 28 times e to the negative 0.01663 times time. But we don't want y, we want t, right? Remember that y of t, right, was equal to t of t minus 44. Okay, so that means temperature is actually going to be 44 plus 28 times e to the negative 0.01663 times time. Perfect. So that means at time 60, which is already hour, right, it's going to be 44 plus 28 times e to the negative 0.01663 times 60, right, it's in the minutes, which is about, so after an hour, it's going to be 54.3 Fahrenheit. Okay, perfect. And then for part B is asking, how long does it take for soda pop to cool to 50 Fahrenheit? Okay, and in our case, we already reached 54, so we definitely need more than an hour, right? So let's actually compute an exact number. So we know that the temperature is equal to 50. So that implies that 44 plus 28 times e to the negative 0.01663 times time is equal to 50. So we're going to get that e to the negative 0.01663 times time is going to be equal to 6 over 28, which means time is going to be negative natural logarithm of 6 over 28 over 0.01663. Going to be about 92.6 minutes, right? So 1.5 hours. So 1 hour and 32.6 minutes. That's how much time it will take. Okay, so, and notice, right? Notice that if we approach our function, right? If we go ahead and say, well, if limit as time approaches infinity of t, right? We're going to have limit as time approaches infinity. What's our lowest temperature we can ever reach is actually going to be 44, right? Because exponential is just going to decay to 0, right? So that's simply 44 plus 28 times 0, which is 44. Right, so that's the lowest temperature we can reach. All right, perfect. And then the last part. So we already kind of did investments and economics in the previous lessons, but now let's remember. So we can technically, do that the same thing as a continuous compound. We give the formula, but we can reiterate it and repeat it. So let's take a look at example. It's going to be our last example. So continuously compounded interest. So let's say if $1,000 is invested at 6% interest, compounded annually, then after 1 year, the investment is worth 1,000 times 1.06, which is $1,060. After 2 years, it's worth 1,123. After t years, it's going to be worth 1,000 times 1.06 to the power of t. So in general, if an amount a sub naught is invested, an interest rate at r, then after t years, it will worth a sub naught times 1 plus r to the power of t. Usually, however, the interest is compounded more frequently than once a year. For example, n times. Then in each compounding period, the interest rate is r over n, and they are n times t compounding periods in t years. So the value of investment is actually this equation. Okay, so however, we can make a continuous compounded equation, right? So how do we do that? Well, a sub t is going to be equal to limit as n approaches infinity, right? So a sub naught of 1 plus r over n to the power of n times t. So what we're going to do is we're going to simplify a little bit. So limit as n approaches infinity of a sub naught times, so it's going to be 1 plus r over n to the power of n over r, then to the power of rt. Okay. Then by using the limit rules, we can have a sub naught times limit as n approaches infinity of 1 plus r over n to the power of n over r, which we've previously done such limit, right? Which is going to be, if we recall, it's going to be a limit as I'm going to say the following. I'm going to say let m to be n over r. So then I will have m approaches infinity of 1 plus 1 over m to the power of m, everything to the power of rt. And so that actually simplifies to be a sub naught times e to the power of r e. Right, this is a special limit. So the differential equation dA over dt will be equal to r times a sub naught e to the rt. Or in other words, r times a t. Alright, so now this is compounded continuously. Right, so now we can use to find equations, and based on the function of the compounded interest, we can develop the differential equation and actually solve it. All right, perfect. So that would be it for this lesson, and next lesson we will talk about the related rates. Thank you guys, and I'll see you next time.